Olá, bom dia a todas as pessoas presentes aqui, a quem está nos acompanhando pelo YouTube. Vamos dar início então ao nosso terceiro dia. Gostaria só de alguns avisos. Então, a aula hoje ela vai ter uma parte online, então logo na sequência vai ser colocado o QR Code, escaneiem para ter acesso aos pacotes, aos scripts que a gente vai usar, tá? Além disso, lembrando, na sexta-feira, então, a gente vai ter as apresentações dos grupos. Hoje a gente deve estar organizando a lista de apresentação. A gente sabe que algumas pessoas também se propuseram a apresentar trabalho, então a gente vai ser de 5 a 7 minutos e meio para apresentar, de 5 a 7 minutos e meio para fazer perguntas ou dúvidas. Então, se atentem a isso, hoje a gente deve estar liberando a questão dessas informações. Além disso, lembrem, todo dia, fazer a lista de presença aqui no QR Code fora, porque para vocês terem certificados, depois a gente vai acompanhar somente quem tem 70% de frequência nas atividades que a gente vai emitir o certificado, tá bom? Bom, então hoje, para dar andamento, né, na sequência das atividades, nós vamos ter a aula do professor Keizun. Thank you for your time. If you can, you are beginning your class. Thank you. If you test the sound, please.
Is this on? Okay. All right. Thank you. Okay. All right. Yeah. Good morning, everyone. It's really a pleasure to be here. It's my first time to visit Brazil, and I really enjoy my visit here. So, what I want to teach today is a session. I think is on your agenda on forest modeling. So, I try to make the teaching material as accessible as possible. So everything that I present today, you can access that through the QR code or the web address. It's a little bit long, so we create a QR code on that. I hope this is also accessible to the audience on YouTube. Okay, so with that, let me put my presentation. All right, so I hope everyone can see the presentation on the screen. So again, the topic today is forest ecology modeling. I use AI. I don't speak Portuguese, but I use AI to translate all the materials also in Portuguese. So you have two tabs in there. Of course, I'm going to present in English, but feel free to click the Portuguese version of the presentation. So. Forest ecology modeling is important for addressing the questions in the Amazon. We focus here on biodiversity and forest change under the global climate change. So first of all, about myself, as Fernando already introduced, my name is Kaizu. I'm an associate professor at the University of Michigan. My research interests include global change biology, ecological modeling, which is the topic that we will talk about today, and environmental data science. I received my PhD in ecology and master's degree in statistics from Duke University in North Carolina in the US, and I completed my postdoc in global ecology at Stanford University in California. And I really want to thank the Fulbright chair, make the connection from the University of Michigan to here, and I will look forward to interacting more with the students and faculty here. Okay, so to set the stage, why do we need to think about modeling in the Amazon? So let's think about the context here, Amazon modeling. So the why Amazon matters and why we use models at all. So to do that, we need to think about what are the environmental pressures? What are the questions that we want to ask? And why we want to use models? And essentially, as I hope I can convince you today, model is a tool for us actually to simplify the problem and how to address them in a more simplified way. So Amazon pressures. So here are the things that at least I read from the scientific literature. The Amazon is changing under multiple pressures, environmental pressures. That includes deforestation. I've heard a lot of stories about that in just a few days in here. Forest degradation, drought, and which is closely related to climate change, and fire. I know colleagues working fires in the Amazon. Fragmentation, more of the landscape level changes. And then on the other hand, we also have tools as ecologists in restoration, and the forest can regrow. How do we quantify? How do we understand that? So these changes are at stake because they matters a lot for biodiversity, for carbon storage, and the Amazon obviously provides a lot of ecosystem services, as well as matters for local livelihoods. Yesterday's plenary session, we heard a lot about Amazon is important in regulating global climate, and that is very true, and that's also one of the reasons why what's at stake, why we need to care about. Okay, so then let's talk about models. Why do we need to use models to think about forests? Forests, it's very hard to argue that forests are complex systems. It is also very slow changing systems. And we want to ask the question, given this complexity, we want to ask the question, such as, will suitable habitats remain? Which species are in where, right? So there's kind of questions that we want to ask, given changing climate. And how fast can forests recover biomass? After the forest is degraded, after deforestation, when they regrow, how fast they can regrow. And another example is that how do the conservation and restoration scenarios, how do we compare one with each other, right? So when we talk about scenarios, I will get to that in today's class. When we get to scenarios, these are the things that have not happened, but we might expect they happen, right? So it would be good to have some kind of expectation to anticipate these changes. So a model, so what is a model? A model is really a simplified representation of a system, often complex system like a forest. So we represent a complex system using a simplified model, okay? That is designed to answer questions like that. So here are the 3 example questions. And therefore, a useful model is the model that the assumptions really match the questions. Okay, so this is something I will come back to the point again. A model, so a common misconception is that the more complex model is a better model, and that is not true. Okay, as I will show you today. Really, what is the best model is the model that can solve the problem, and really depends on the problem, the kind of questions or the problems that you have. So again, a useful model is the one that whose assumptions match the questions. And it is not necessarily a complex model. Okay, so there are many types of models of how we think about forest. But in general, I would like to summarize them as what we call a workflow. So a workflow is a process, when you let's say when you cook, you have a process. You start put one thing first and another thing, in sequence. So modeling workflow, you can see 2 colors in here, and then arrows. The top color, the blue color, is the computation. So that's what we put on the computer. Okay, we will get to that. We will use R. So Thiago did a boot camp last week on basic primer on R. So we will use that as a tool. And then the pink boxes on the bottom, so these are the reasoning. Okay, so this has nothing to do with computer. This is what questions that you ask, how would you like to design your study? Okay, so we always start with question. So that is the box on the left. Okay, so first you have a question, say 3 examples that we just had. And then with that question, you start to collect the data. So collect data can include you directly collect data. You go to the field and measure a bunch of trees. That's one way to collect that. And also we can collect data indirectly. So for instance, yesterday Dimitri's presentation talks a lot about remote sensing. Of course, you're not going to fly your satellite by yourself, right? So you collect the data indirectly. So that's collecting the data. And once you have the data on hand, you are going to put a bunch of assumptions. Okay, so the model is a collection of assumptions. So that's going back to here. Okay, so when you have assumptions, it doesn't have to do with computer, right? So this is something that you can write down with pen and paper. So with those assumptions, then you start to build models. And when you build models, you need to write code. You need to do in R, in Python, in whatever language. Okay, and then when you run the model, you have different scenarios. Again, scenarios are the situations that you would expect. For example, scenario could be the business as usual. Nothing has changed. Or a scenario could be something like let's restore the forest and see what happens. Okay, so you set some scenarios, and you run them. Okay, and you get some results. And then going back to the reasoning, going back from the top blue boxes to the bottom pink boxes, and then you want to interpret. Okay, you want to explain what the model runs. So you get a bunch of output in computer. It could be graph, it could be numbers. How you interpret that. And quite often, this is a cycle. So then you go back, and then you revisit the assumptions that you put on. Right? So the assumptions, for example, you will assume how forests grow. That's kind of assumption. And you want to revisit that. And you may or may not want to change that. Okay? And then, so that's going back from the interpretation to assumption. And sometimes if you change that, you have to run the model again, right? If you change the assumption, then the model has changed. You run it again, and then see the results, interpret, and go in this circle. Okay? And if you are happy with all the process that you have done, and then you take a look at the results, and then go back to the question. Then you answer your question. Okay, does it make sense? Okay. All right, so that's kind of very general introduction of why we need use models and the modeling framework. So now I want to talk about more specifically to forest ecology models. I want to introduce 3 families of models. So these are the 3 types of models, like very broad categories of models that pretty much covers everything that is used in forest ecology. So they target different questions, they use very different data, and they use different assumptions. So again, we're about to survey the field before narrowing down to what we will exactly actually build today. Okay, so this is the table that I introduced the 3 families of models. I begin with 3 questions. Okay, always start with your questions. Okay, so the first question is that where can species of forest types occur? So this is more like a geography type of models, like we have a lot of GIS and remote sensing yesterday. So the tool to address questions like that, for example, what are the particular species occur in somewhere in the Amazon, okay, and with climate change, where the species might occur in the future. So this is a question that fits the first one, right? So now, if you have questions like that, you are really looking at the type of model called species distribution models, or SDM, and there are other names for that, climate envelope models, etc. So the basic idea is that you find the correlation between some kind of environmental variables, like climate, soil or whatever, with the presence or absence, or sometimes abundance of individual species, and you build a relationship between them, and then you project into the future. Okay, so that's the first type of question, and first type of model. The second type of question is forest growth. How do forests grow? How do they die? And how do they recover and store carbon? And for these type of questions, we want to use the right tool for this is forest dynamic models, or sometimes it's called forest demographic models. So demography is the process, growth, mortality, recruitment. This is called demography. This is the second type of model, second family of models. The last one is if you have the last type of question is that you want to ask how do climate, carbon dioxide, water, and physiology, things like that, environmental variables affect the forests. So if you have questions like that, you are really looking for the model family of process-based ecosystem models. So these models are basically physics. How do you use the environmental layer to inform forest change? I put a final note, the final line here. No one model families does everything. There's no single tool can address all of them. It really depends on what kind of questions that you want to ask. Okay, so a little bit briefly on three types of models. The first one, species distribution models. So a typical question that you can ask with species distribution models is that where is the environmental suitable for a species now or in the future, right? So for instance, if you want to if you want to understand the range maps of a particular tree species or animal species, this is the distributional model. So the data for such a kind of models are you need occurrence records. You go to sample, you find a species, and you record the geographic location of that species. So that's occurrence records, okay? And you need environmental data such as climate, soil, topography, land cover. Use remote sensing, to retrieve that. The basic idea is that the occurrence of species is a function, has a relationship with different environmental variables. Okay, so you need that. And then you put these data into species distribution models, and then the output of that, it will produce habitat suitability maps. I just mentioned range maps, right? So similar idea. You have some kind of habitat suitability. And then it can also tell you the current distribution, geographic distribution, as well as future distribution, because we have a lot of climate projection. So basically, you are using climate projection to feed into the model, and the model will output the potential predicted distribution in the future, given the changing climate. Okay? So how many of you have heard of this concept of species distribution model? Some of you. Yeah, great. Okay. So I want to add a comment on this again. There's no single model that wins all, right? There's no single model that can do everything, and that's the only model that you want to look for. So all the models have their strengths and limitations, okay? So the strengths of species distribution models are that it's very intuitive, right? It's basically presence-absence of species, and then you have environmental layers. It gives very visual output. It usually gives you maps. That's very easy to see, okay? It is used a lot for biodiversity modeling, biodiversity planning, because essentially these data are the ones that you use for biodiversity monitoring, okay? And it's relatively accessible. There are so many tools nowadays that, including a lot of open source tools that you can use. The limitations of that, however, is that this is something that often get confused. When we have a species distribution models, what it does is that it models what we call suitability. Okay, so it's not exactly the species presence absence. So there's not a guaranteed presence. Because there are a lot of, so get a little bit technical detail here. There are a lot of sampling issues. Whenever you deal with biodiversity data, you have a lot of sampling issues, simply because you don't see all the species all the time, right? So if you go to forest, you want to find particular animals, what about the animal is not there? You can't say that the animal cannot live there. It's simply because you don't find it. Okay, and even for plants, given the hyperdiversity in the tropics, in the Amazon, you can't really exhaustively sample everything, even for plant species in the forest. And of course, you don't really have the resources to sample, every inch of the land, right? That's impossible. So you have a lot of sampling issues, and therefore, SDM, species distribution models, there's no guarantee that it will tell you the exact presence. It gives you some kind of model suitability. So that means when you project this into the future, okay, so you are essentially project the suitability. Okay, so you're not really presence. There's a very important process going on here, which is quite often ignored in this type of model. That is dispersal limitation. We know the trees, dispersal has limitation for even for animals. You're not going to disperse. When you have a suitable habitat, doesn't mean that animals can get there, right? Also, this type of model basically ignore biotic interactions. When you have species A, so you build a model for species A and build another model for species B, and so on and so forth. And if you want to ask a question, what is the richness into the future? A common way to do this is to stack them. Okay, and that is not quite right, because if you think about this, if you build species A, you are basically ignoring species B, C, and D, right? So there's no sort of biotic interaction whatsoever in this type of models. There are some, recent advancement. I'm happy to talk about this in the Q&A on that. But in general, this type of models don't consider biotic interaction. So that means the projection can be off, right? And then the other limitation is that it generally does not consider disturbance. So it assumes, so there's a building a relationship between species occurrence and the environment basically assume what we call equilibrium. Okay, so everything in the presence absence is in the equilibrium of the environment. Okay, so this is okay if you don't have a disturbance, but what about if you have a huge deforestation? And that's a huge disturbance. So that will disrupt this equilibrium assumption. So equilibrium is assumption in the model. It breaks it. Okay, it breaks it, and it may affect the results that you get from species distribution models. And then finally, sampling bias. I already talked about this. Whenever you are dealing with biodiversity data, you got to be careful about sampling, right? So are you actually, get the data that what the actual ecosystem has? So these are the kind of the common misconceptions in the species distribution model. Okay, so the second model family, which we will spend the majority of time of today to work on, is forest dynamics, or sometimes called forest demographic models. So a typical question that you can address with this type of model is, given a certain piece of forest, how do they grow? How do they die? How do they recover? Recruitment, and how do they restore store carbon through time? Okay, of course. So dynamic means change with time. Okay, so all of these variables will change with time. So that's why we call it dynamic. And demography means the process, the population process, growth, mortality, recruitment. So the processes that go into this model include, right, I just mentioned that growth process, mortality, is how trees die, recruitment, and disturbance. A very common use of this type of model is to look at disturbances. And then recovery, okay, we will have examples like that. And in ecology, we also call this succession. Okay, you have primary succession, secondary succession, how forests grow, and for both individual species and for communities. The data for such a model is no longer species occurrence. So the data that feed into this dynamic model, forest dynamic models, are typical forest inventory data. So forest inventory means that you measure individual tree, the DBH, the status, and you track that over time. So time is important. We need to get a temporal component in this type of questions. Growth, mortality, disturbance histories. When disturbance happens, how big, how severe. This is the family of models that we will actually build today. That forest inventory plots are the classical data sets, and including a lot of the efforts that happened in the Amazon. So the strength of such a model is that it connects directly to inventory data, which is readily available in a lot of applications. It represents the change through time. That's where the dynamics comes in. And it supports the scenario comparison, so you can tune the model. This is actually one of the great use of the model, is that you can set up a scenarios and run the model and see the output, right? And then you change scenarios, you see what's different set of output. And it also makes the assumptions explicit. The limitations, though, for such a model is that not all the demographic processes are equally parameterized. So some of them are more complex, some of them are simpler. So things like mortality and recruitment, these are pretty hard things to observe. And the reason is very simple. If you're given a certain number of tree species or individuals, only few of them will die, right? So that means that by nature, you are limited by data. So when you parameterize the model using the focus on mortality, then you have a limited data to work with. The same can be said for recruitment, okay? And disturbances. These are pretty hard to predict. The parameters may not transfer across regions. So what this means is that you can build a model that runs nicely in this certain part of Amazon. And if your colleague asks you, can you help me to predict the forest in a different part of Amazon, it may not work. Okay, because the forests are different, and if you don't have the data in another parts of the region, it may not work. Okay. So the third type of model families, the last type of model family is the process-based ecosystem models. So these type of models typically address questions like this: how do climate, CO2, water, energy, and physiology affect the forests? Okay, so this is as I mentioned before, this is basically physics. Basically, you have environmental sort of abiotic factors. How do affect the forest change? The processes that go into this model include basic physiological processes. Photosynthesis. How do plants fix CO2 in the atmosphere and convert that into sugar, right? Basically. Respiration, which is the reverse process. Evapotranspiration, so it's a combination of evaporation and transpiration from the ecosystem. So this is hydraulic. And carbon allocation, when you have photosynthesis to take into the system, how do plants allocate them? How much goes into the leaf, how much goes into the stem, how much goes into the root. Soil, water, and carbon dynamics. Again, a lot of physics here. The data that go into this type of model are typically climate forcing, so temperature, precipitation, drought, soil data, plant traits, functional traits. We had a presentation yesterday on functional ecology of plants. Remote sensing can also play an important role in here because we can get a lot of data by using remote sensing. The strength of such a model is that it explicitly represents mechanisms. So everything in the processes, this is what we call mechanisms. Okay, photosynthesis is a mechanism. We know that will work, right? Because if you're a plant, you have to have photosynthesis, right? That's how the plants grow. So it links ecology explicitly to climate systems, and that is actually used a lot in Amazon, in fact, to understand the vegetation here. It is usable under novel future climates because a lot of the physical law here that will hold. The photosynthesis will still work, right? So it doesn't really, in the future, you might have a different condition, but still plants have to photosynthesize. The limitations, though, is that these type of models are often complex, much more complex than the first two type of models that we just talked about, which makes it very hard to run. So sometimes you can't even run that by yourself. You can't run that on your computer. It has to be on a cluster on a supercomputer. It has a lot of parameters, so we are easily talking about hundreds of parameters, And that makes sense. Comparing to a forest dynamic model, you have a handful of them. It's much easier to parameterize. But for those type of models, you have so many parameters, so it makes it hard to parameterize. If you cannot parameterize the model, you can't even run it. Okay, so that's not very useful if you have such a complex model. It is also very hard to validate. So validation means that you have some kind of output from the model, and we want to see how close that is to reality. Okay, you can always crank out numbers from models. Right? It's kind of like a computer game. You can always crank out numbers, but whether or not the numbers make sense, whether or not they are accurate, that needs more thinking, right? You need to validate that, and this type of models are very hard to validate. They are also sensitive to uncertain mortality and disturbance processes because we don't really have much of data on that. So examples like DGVM. So you might have read this in the literature: dynamic global vegetation model, DGVM, or land surface models. Land surface models are the model that actually feed into Earth system models that are used for climate projection. So I begin with Amazon is very important for climate regulation. How do we know that? So the knowledge comes from models like this. So land surface models that feed into the Earth system models. So this is the last model family class. Okay, so for today, we obviously we can't talk all of them, so we will choose and focus on a single family of models to understand the system. So as always, we want to, we have already surveyed the field. Now we want to narrow down, and we want to always start with the question, not the software. Okay, a common misconception is that let's start with a particular type of model. And that's not really a very productive way to do this, but let's think about what questions that we want to ask. So again, the three model families for species distribution models, the main question is where is the suitable habitat? The typical data are species occurrence data, climate, soil, and land cover. The key assumptions that we use those type of model is the environment occurrence relationship. The forest dynamic models ask questions like how does the structure of the carbon change over time? Okay, dynamic. And the typical data used in those type of models are forest inventory data, forest growth data, mortality disturbance. And the key assumptions here are the gross mortality disturbance rates that represents the future. And the last full model class, process-based ecosystem models, are questions explicitly ask how do forest ecosystems respond to climate, and the data that they use are climate forcing, soil trace, remote sensing, and the assumptions are the mechanisms, like photosynthesis, respirations. So each model is assumption machine. The question is where the assumptions are useful. So we really need to define the question and think about where we want to use them. Okay, so again, you might ask, given these choices, which model, the three model family classes, which model should we use? We should always start with a question, not the software, not the data set, not the fanciest method, not the most complex model. So you want to ask yourself, what decision, comparison, or ecological process do we need to understand? And then choose the simplest model that can answer that question responsibly. Okay, so for today, I want to focus on the second model family class, which is forest dynamics model. And forest dynamic models are ideal for this workshop for a couple reasons. First, these type of models are very transparent. So transparent means that you can easily understand what is going on in this type of models. The assumptions are visible. We'll talk about different assumptions and how they how you actually implement this in the code. And they are easy to reason about. So you can question about these assumptions, and if you want to change them, you can make corresponding changes in your computer code. These type of models are very much data grounded, so it directly tied to forest inventory, which is the primary data that used in forest ecology. And lastly, the reason for us to focus on forest dynamics is that it's what I call trackable. So it's very easy to see the code in R and change them and then iterate what we have done. Okay, so for today, I hope by the end of the workshop of today's class, you'll be able to achieve the following learning objectives. First, I hope you can explain how forest biomass changes through different demographic processes, growth, mortality, and disturbance. And second is that you should be able to build a simple forest dynamics model using the inventory data, okay? And then use that model to project the biomass and carbon forward through time. And also under different scenarios that are relevant to the Amazon. So we can have a baseline scenario, which is nothing changed, and see what happens in the next 50, 100 years. We can have a drought scenario. Let's say if we have a reduction in the rainfall, what will happen? We can have a degradation scenario and restoration scenario. And then coming back, lastly, coming back with different scenarios and different model outputs, think about model assumptions and limitations. So these learning objectives directly map to what we'll code in the notebook, and I will walk through you today in the morning, both in the morning and also in the hands-on session in the afternoon. Okay. So logistics. So for today, I was basically a rough workshop agenda. So we start with a big picture. We already accomplished that. 3 model families. And then we will have so I have a separate notebook, which is available in here. So we will walk through that, line by line, and show you. So start with what kind of data that are typically needed for forest dynamic models. And these are the forest inventory data, okay? And after that, we will build a very simple biomass dynamics model as an example for forest dynamic model. And we'll have a little bit break. And after that, after we have the data and the model, and we will set up different scenarios. We'll have land use scenarios, as I just introduced, baseline scenario, drought, etc., and then we'll build them, run them, visualize and see the output, and then compare different scenarios. And finally, we will interpret that. We will look at the results and interpret and think about the assumptions and limitations and discussion. So what I plan today is that I hope in the morning I can walk through that relatively quickly. And then I also have a lot of discussion points and exercise and questions in the notebook. If we have time, we can talk about that. But otherwise, we can leave that to the afternoon. I really want you to able to actually run them. Again, everything is available on the notebook in both English and Portuguese. If you are more comfortable with Portuguese version, you feel free to take a look at that. Okay? Any questions on so far on the logistics, on the big picture? Good? Okay, great. So just to get us started, so this is the model that we are going to focus on. It's actually pretty simple. So we will build a simple biomass, or we can call this carbon dynamic model with one single equation. Okay, so here the B represents biomass, and subscript T represents the biomass of year or time T. Okay, make sense? It's how much carbon that you have in time T. So what this model says is that here is where the dynamics comes in. The biomass of T plus 1, which is like next year, is biomass of time T this year plus the growth component. Okay, so that's G sub T. That's growth minus the mortality, minus how much trees have died in this period from T to T plus 1, and then minus the disturbance. Okay, it makes sense? It's like you have a bathtub of water. How much water that you have in the next time step depends on how much water comes in and how much water goes out, right? Same idea. The biomass of next year depends on, of course, first depends on how much biomass you have in this year, and then how much comes in, how much goes out. And then the amount that comes in is the growth, because tree will grow, right? Makes sense? Tree will grow bigger. And also you have the new trees coming in. But on the other hand, some trees will die, so that reduces the live biomass pool of the ecosystem. And sometimes you have disturbances, so disturbance will kill some trees in a different way. So biomass of next time point depends on the biomass of this time point plus the gained biomass and minus the lost biomass. Okay? So what we will do today is that we will look at a sample forest inventory data set. And in fact, I'm actually going to simulate that. So it's not real data, but it's similar to the kind of data that you will collect in the field. So that data set includes variables like dBH. So dBH is diameter at breast height. When you go to the forest, you measure how big the trees are. It includes wood density, and wood density is a critical variable for you to convert the dBH to biomass. So basically, you have dBH, you have allometric relationship, allometry. Okay, have you heard of this word, allometry? Allometry, right? So we'll talk more about that. So allometry is that you have the size of the dBH, and then you estimate the volume, but then how do you convert this to mass? Because biomass is a mass, right? So there's a density. So we have that, and then we calculate, so then we summarize the plot level biomass, because what you measure are individual trees. What you care about, okay, so this goes to the question. Your question is not individual tree, right? Your question is about the forest. So you have to think about the whole forest. How many trees, have large trees, small trees. So then you calculate the plot level biomass. And then you can project forward using the dynamics equation right here. So you have then you have B, biomass variable, right? Coming from the forest inventory data. And after that, you set up a few scenarios. So you have baseline scenario, drought, degradation, restoration, and then you visualize. And quite often, when you get to step 5, you will go back. Okay? You will say, wait a minute, is my assumptions really valid? So should I change something? And you will tweak that, and then you rerun the model, and then you see the results. Okay? So this is also connected to the workflow box plot that I presented earlier, right? So you have the reasoning components in blue, and then you have the computing components boxes. So everything that we will do here is the same idea, and we will gradually migrate in code. We will use R to do everything that we're talking about here. Okay, so the workshop material, so you have this. I hope, does everyone have access to the material? Okay, good. Okay, so this will direct you to a web page, and the web page has linked to this slide deck, exactly what I presented here. So there are basically two themes. There's a notebook, it's a web page, and then the slide deck here, which is also HTML page, available in both English and Portuguese. So we will work through the notebook section by section, and then we will make minor changes to compare the scenarios. So what I want to ask you is that as you go through this process, always ask yourself, what ecological assumptions does this line of code represent, right? Because eventually we will go into write code, right? But it is your responsibility to think about there are different assumptions underlying each line of the code. What kind of assumptions this line of code represents. So I hope by the end of today, I really want to convey this take-home message that there is no single so-called best forest models. Okay, only ones that is more or less appropriate for a particular question that you want to ask, the kind of data that you have on hand, and the decision context. What do you want to achieve using, what do you want to make the decision on? So today, we begin with a transparent model of forest change through time. This is by no means saying that this is the only model that you will work on. Rather, this is only a start. Just give you an example. So, so before we begin, let me just open up a floor on the questions before we begin, and then we will take a short break before we transition to the notebook. This is the last slide. What kind of forest change questions, okay, again, let's start with questions, are most important for your work, in your interest? So here are examples. Biodiversity loss, it could be carbon recovery, drought vulnerability, degradation monitoring, forest restoration planning, and protected areas. Okay, so I will stop here. I'd be happy to hear your comments, and then after that, we will take a very short break. We are about 10 a.m. in here. Maybe let's take a 5-minute break or something like that, and then we'll come back to the notebook to work through the whole process and focus on the forest dynamic models. Okay? Any questions? Any comments? Yes, please. Yeah.
Oi, foi.
Oh, hi, Kai. I have two questions about the SDM, in fact. You say that SDM is not good, for example, if you want to see the species, the multiple species distribution, right?
Mm-hmm.
If you have to see the distribution of multiple species, you have to perform one model for each species, right? Because they don't have a way to consider interactions about the species, species interaction.
Right.
I think these guys that create these models, the SDM, also create the JSDM.
Right, yeah.
Is that one that modulate that consider species interaction or not? This one consider?
This is a great question. So what you mentioned is a specific type of SDM. Is called joint species distribution models. I was in the early phase of development of these back like 10, 15 years ago, these type models. So I guess the answer is somewhat. It's because this is still kind of controversial topic. What JSDM does, so the difference between SDM and JSDM is that SDM is a univariate model. So you have a single species, and that's what we call, you have a vector, univariate. JSDM is a multivariate model. So you have matrix as a response. So it considers the correlation, these are statistical or machine learning models. So everything here is correlational, okay? It considers correlation between the either presence, absence, or abundance of each individual species. So that somewhat addresses that. But then there are also other scholars argue that the correlation that they address is not really a biotic interaction, right? If you have a biotic interaction, typical way to do this, if you have a microorganism, you put that in a petri dish, you grow them and see how they interact, right? And these models don't do that. These models simply take a big data set. So somewhat.
Yeah. So I think it's a part they consider, but it's not the true interaction, right?
Right.
Yeah.
Right.
Okay. I also saw to read a little bit that they also published in Ecology, I think last year or in the beginning of this year, the JSTDM, that is jointly species trait distribution model. Mm-hmm. They also consider species traits. So, but I think it's also about correlation.
Right.
Like, for example, if you have like a given species, like an invasive species that is present in one place, they can correlate with the probability of this another species that have a particular trait to occur or not occur.
Right.
So I think it's, but I also think that it's about correlation, it's not interaction itself.
Yeah. Again, I think they are moving to that direction, which is I think is great direction to move to. But again, fundamentally, this is all correlation.
Yeah. Thank you.
Yeah, thank you. Any other questions?
Mais algum comentário? Dúvidas? Não? I think it's okay.
Okay, let's take a break and is that 5 minutes, 10 minutes?
10 minutes.
10 minutes? Okay, let's take a 10 minutes break and then we'll come back and we'll work, get your R studio started. We will start to code. Okay?
Perfect, thank you.
Okay. All right. Hello, everyone. Everyone hearing okay? Okay, so again, use either the QR code or the web address in here. So then you can access the exact same web page that I'm showing here. This is a notebook that we will work through for the remainder of the class today. And again, I'm trying to make this as accessible as possible. So I have both English version, which is this one, and if you click the Portuguese version, that will lead you to a, I use AI to translate. I hope that's accurate enough. So everything is translated into Portuguese. So there's that, and then you can also click the slides in here, which will get us to the slide that I just presented in the past hour. Okay. Yeah. So this is the Portuguese version of that. Again, there's a translation, different versions in here. So we will use R and R Studio for the coding part. Does everyone have access to that, R and R Studio? Okay, who doesn't have access to? Okay, so Thiago did a very good job in bootcamp. So we'll use that, and we'll use Tidyverse, and that's the only package that we will use today. The notebook is organized, as you can see from the table of contents. So we will start with some intro, and then we have essentially 3 sort of big sections that are relevant for today's class. We'll have forest inventory data. So here, I don't have a actual data set, but I simulate. So I make a data set that is similar to what we'll have in the field. And then we'll build a model, build a biomass dynamic model, as you just saw on the slide. And then we will use different scenarios to run the model, and then we will interpret. Okay. So this is a hands-on workshop on forest ecology modeling, and we focus on forest dynamic models out of the 3 model family class that I introduced in the last hours. Okay, we have species distribution models, forest dynamic models, and ecosystem process-based models. But we will focus on forest dynamic models. And we can ask questions such as how fast can forests recover, how much carbon might be lost under the tree mortality scenarios, how do deforestation, degradation, and restoration scenarios compare, and then, as always, think about what assumptions are going in underneath all these models. The goal here, of course, is not to build a perfect model of the Amazon, but to understand the basics, how ecological models are structured, how do we think about scenarios, how do we set up scenarios, and how do we implement them, and how do we model outputs can support our conservation decisions. Why model forest change? This is kind of reiterate what we have learned in the last hour. It's really a simplification of the system, and then we can play with that on the computer. Learning objectives, you should be able to explain how forest biomass change through the 3 demographic processes, growth, mortality, disturbance. You should be able to build a simple forest dynamics model using forest inventory data, and project the biomass and carbon forward through time. Again, dynamics means time. So time is it's the key of all types of dynamic models. So we want to think about the change over time. And you should be able to compare scenarios that are relevant to the Amazon forest, including baseline, drought, degradation, and restoration. And then finally, recognize the model assumptions and limitations. Okay? So this is a draft agenda. Okay, so let's think about forest inventory data. Before that, we need to set up the R environment and Tidyverse. So how many of you have heard of Tidyverse? I guess at least from Thiago's bootcamp. Okay, so many of them have done that. So the first thing that you need to do to run this is to get that installed if you have not done it already. If you have that, then you can skip this step. And the way, so Tidyverse is a collection of R packages. So Tidyverse is not a single R package, it's a collection of them that are really, really handy. And I would say that it basically changed everything in the R environment for the past like 10 years. That they share a common design philosophy, so it makes things very streamlined. Everything is very consistent, and change the data, the design and the syntax. So we will use this for data wrangling. Data wrangling means that you want to reshape the data one way or the other. This is specifically used in dplyr package within the Tidyverse family. We will use ggplot2 for plotting. We will use PURR, P-U-R-R-R, for functional iteration. So we'll write functions, but we'll write iteration in a more efficient way. Okay, this is much better than base R, the old way to do this. And we will use Tibble for data frames. So Tibble is the more advanced version for data frames. So here is the code block. So get on the web page. If you put the mouse cursor in here, what you'll notice is that there's a small clipboard in here. So if you click this, this will copy the whole thing to your clipboard. And then, let's see, can I open up my RStudio? This is my RStudio. You should have a similar interface like this, right? So you can either paste that directly to the prompt in here. Oh, okay. Is it big enough? Okay. So either you can paste in here, but I think better is that you can create a project, or you can start a script. Okay, so you start our script in here, so then it has a file. Okay, make sure that you save them. Let's say I save this to forest modeling. Let's call that. Okay. So that will save this, and you can paste. Okay, right-click and paste, or Control-V. Right, so this is exactly what you see in the code chunk in the notebook. You paste in here, and then Control-S to save it, so that you have a copy. Right, next time you don't have to do this again. And this is the whole, strength of scripting language is that it's reproducible. So reproducibility is very important. Okay, so there's that. So so this is basically checking whether or not you have that. And in fact, I just installed Tidyverse on this computer, so it doesn't really install that again. But if you run this 3 lines of code, it starts to install things. That means Tidyverse is not on your computer, so it has to install that. Okay, so after that, you load it. Okay, so load that library, Tidyverse. It will get you a bunch of messages. Okay, so that's basically the workflow that we will have. So we will have code chunk in here. And you should be able to copy this either in this way, or you can select, copy whatever things that you want, or you can type if you want to type. Okay. So that's the setup. Now, after you have the Tidyverse set up, we will create a synthetic inventory data set. Okay, synthetic means that it's not actual, but it's it's similar enough that it's kind of like actual data set. So forest inventory data often has measurements of individual trees in a plot, right? So a common variables in the forest inventory data set includes you need to label plot, right? This is plot 1, plot 2, that's the plot identity. And then for each individual tree, you have the identifier for tree. This is tree, 1 to 3, tree 1 to 4, tree 1 to 5, right? Individual tree. And typically you have some kind of species or functional group information for that particular tree. Okay, not all the species are the same. And then for each individual tree, you have the measurement of diameter at breast height, or DBH. You go to the forest, it's about 1.3 meters, and you measure the circumference of the tree, and then you get the DBH of that. Sometimes you have the height measurement, which is useful, but it's a little bit hard. You need to use LiDAR to measure the height, or use other ways to do that. And then wood density, it can, so typically this type of data, wood density is coming from external data set. So you have some kind of big table, each line, each row is a species, and then the wood density is a kind of empirical value for that species. So a lot of people have done this type of work. You also need this type of forest inventory data usually have a status, so live or dead, and that's important, right? When we think about forest mortality, that means this much of biomass or carbon moved from the live pool to the dead pool, right? You need to track that. So for this workshop, we will use a small synthetic inventory style data set that organized 4 functional groups that are commonly used in the Amazon tree communities. So first we have fast-growing pioneer species. We also have slow-growing shade-tolerant hardwoods. So this is the successional gradient. And then we have palm trees, and then long-leaved emerging canopy trees. So as I said, this is just meant to give you an example. This is not the actual data set. The values are illustrative, not the measurements from specific plots, but I try to simulate them similar to an actual data set. So here is how we simulate data with R's function. So we will do this stochastically. So that means we will generate random numbers. If you know a little bit about R, so R has a family of functions that generates random numbers. They all start with little r. Okay, so we have the R gamma is the gamma distribution, R norm is the normal distribution, R unif is a uniform distribution, and the sample is the taken sample from the data that you generated. Okay, so we'll do that. And then we will control the functional group composition and size distribution. So size distribution means that imagine that you have a histogram. In fact, we have that in the notebook. The x-axis is the size, how big or how small, and then the y-axis is the count, relative count. And then we want to make sure that the patterns that we explore, for example, wood density differences, show up clearly. And the other thing I want to note that is, so when computer generates anything in stochastic sense, so generate random numbers, it's not actually generate random numbers. It's something called pseudo-random numbers. Okay, so sometimes it's the clock of the computer, etc. Now, it's okay that you just do that, straightforward with the R functions. However, I said one of the principles of data science is reproducibility, right? If you want to compare results that you do it now versus you have a colleague that they are doing their thing, or just compare with yourself. Let's say 1 month after today, you want to repeat the whole thing. And you want to make sure that everything that you will repeat months later is exactly what you have that for today. We recommend you set the seed. So when you set the seed, then the number that you generated will be exactly the same. Okay, so this is just a tip in when you run models. Okay, so that's I set the seed. You can set whatever arbitrary number in here, but with that purpose, so that the whole whole workflow is exactly reproducible. Okay, so to simulate that, this is actually one line of code. If you look at closely, I didn't really. This is a very long line. I have a line breaking here. What this does is that it creates a table, which is the kind of the more advanced version of data frame, with a bunch of variables. And all these variables are commonly used, commonly seen in the forest inventory data set. So first we have plot ID. You label the plot. So then I have the plot ID start with plot as a prefix. And then I have 6 plots. Each one of them have 50 trees. Okay, I repeat this 50 times. So page 0 is concatenate the string here and then numbers here. Okay, so that's plot ID. And then I have tree ID, and then I have trees, and then 1 to 300. So I have 300 trees in here. And then functional groups. So here, the sample is taking a random sample of the data that I created. So what I did here is that I have a size of 300 because that's how many trees that I have in this data set. 6 plot, 50 per plot, so that's 300 in total, right? 6 times 50 is 300. So 300 trees in total, and I randomly draw them of 30% pioneer species, 35% shade-tolerant hardwood species, 15% palm, and 20% emerging canopy hardwood. Okay, so again, this is a data set with 300 rows. Each row is a tree distributed across 6 plots. Okay, each plot has 50 trees, and they are 30% pioneer species, 35% shade-tolerant, etc., etc. It makes sense? So that's how I create that. And the next variable is DBH. It's diameter at breast height. So I use a gamma distribution to simulate that. So this is a 300 is the size. So the gamma distribution has 2 parameters, a shape parameter and a rate parameter. So gamma distribution is positively defined. So it means that everything that you generate from a gamma distribution will be positive. Okay, and this is set the rate of the parameter. We can talk about details of that. Gamma distribution is different from normal distribution. If you have normal distribution, is everything can be from minus infinity to positive infinity, but gamma distribution is all positive, which makes sense because DBH can never be negative, right? You can't have a negative DBH. And then I have the height here. So height here, I simulate this as using a normal distribution, mean 20, standard deviation of 6, and then Pmax is getting the parallel max. So the cap of either 3, I cap them as a 3. And then the wood density, this is where I set the density. So this is a row in the wood density data set. So this is a uniform distribution, 300 trees, drawing from, if it's a pioneer species, then the wood density is somewhere between 0.3 and 0.45. I actually did look at the literature. This are the empirical values for the wood density. So set that this is depending on different functional groups, and that's the wood density that we have for each individual tree. And then last one is the status. So it's alive or dead. Okay, so again 300, and then with replacement. And roughly, I have the probability of 92% live, 8% dead. Okay, that's the status of the tree. So once you've done that, so this whole line here, that's the forest inventory data, and you type the object name again, this will give you an output, right, of the data that we just simulated, the data that we just created. So you can see here, plot ID is plot number 1. Of course, there are 300 rows. This doesn't show everything on the screen. You can view this in another way. And then each plot, I have 50 trees, in total 300 trees. And then functional group, this is kind of randomly draw from that, sample from that. DBH is the value that we created. Height is the value that we created. Wood density is a kind of empirical value. So this is not purely random because it depends on the functional groups. And then the status is we randomly draw with 92% live and 8% dead trees. So just give you some Amazon context. The pioneer species now grow fast and usually have low wood density. That's how I set up my code to do that. The emerging canopy trees, something like Brazilian nut, are long-lived, dense wooded, so the wood density is higher for these trees, and then store more amount of carbon. Palms have a distinct growth form with no secondary wood growth, but simplified here as a wood density group for the teaching purpose in here. Any questions on this? How are we doing here? Are you able to run this? So just very simple is you can click this. Okay, so getting back to our studio, right? Paste here. right? Save it. Run this. You can press Control and return, or if you use Mac, that's a command and return here, right? So I set the C, and that's simulation. It's very fast because it's pretty simple. And then you type the name that gets you the data set. That's here. If you use the R environment, you can also click this. This will give you a view, data viewer in here, right? If you use R Studio, that gives you the whole thing. It's actually goes all the way to 300, 300, in here. Are you able to at least understand what we are doing here? We will have more time this afternoon to work this in a hands-on session. Okay? Okay. Okay, so that's that. So after we kind of collect, really what I collect the data means that I simulate the data on the computer. We can explore the data. So first, we inspect the distribution, the diameter distribution of the forest. So what we do here is that here I use the forest inventory data that we just simulated. It's the same object. And I pipe them in. So, okay, pipe is it's a very handy tool. So in R, in the new version of R is vertical line and the greater than as a pipe. So what this does is that it makes this the first argument of the second function following that. Okay, so you can write this as the same thing, ggplot and then forest inventory, comma, AES, it's the same thing. But this is, I kind of like this because it's syntax speaking is easier to understand. It's also easier to debug your code. So we focus on this object and use ggplot to make a graph. Okay. So ggplot has a few things in its grammar, in the syntax. So it maps the aesthetics. So dBH in centimeter, which is a variable in here, right? So that's this guy, this variable in this data set. We focus on this variable and we want to put that on the x-axis, okay? Because we want to create a histogram, you can see here. This is what we want to do. So this diameter at breast height, that's dBH, that's on the x-axis. And then we put a geometric layer on this. We want to plot a histogram. Okay, a histogram is the frequency distribution of that. And we want to set 30 bins. Okay, I mean you can tune that, but I find 30 bins is reasonably well represents the data set. And set the color, fill and color, and then set the theme, just make it look nice. And then take the labels of that. Okay, put a title and XY label. So that gives us in here. Okay. So, any questions on this code? So let me ask you, when you see this, what can you tell? What ecologically, what does it mean to you? Do you see a lot of big trees, small trees? What does it tell you? Anyone?
Or medium tree? Oh, sorry. Like we have a more small and medium trees and less bigger trees, right?
Yeah. So right. So when you look at this, the way to read this is again x variable. The horizontal axis is the size, right? And you look at the height of the bar, right? So what this does, what this shows is that we have a lot of 30 centimeter-ish, 30 is like this big trees. Okay, that's the tallest. And then we have more of the small trees, but few large trees. Right? So this is what the histogram can tell you, the size distribution, which is very important. Because when trees grow in a forest, what it does is actually moves the distribution from left to right, because it grows bigger, right? And some of them will die. This shows the kind of the age or the size distribution of the forest. So here, this is relatively early-ish successional forest, as opposed to if you have a lot of large trees, that's kind of like late successional forest. Okay, so that's what this histogram tells you. And the code here is how you make the histogram. Okay, as we explore the data. Now, we can also do this by functional groups. I already give you a hint here. We want to have 4 functional groups because they are different, right? Palm tree is not the same as, late successional hardwood. So, and the way to do this is, this is actually one of the nice things about tidyverse and ggplot is it's very consistent syntax. So we want to create something like this. Okay, so this is our end result. Now, instead of lumping, so this figure lumps everything regardless of the functional group into one graph, right? But now we want to look at them in each individual functional groups, and we have 4 of them. So to do this, we call this facet. So pretty much everything here is the same, except that we add one line here, facet wrap. So we wrap them, facet, as a function of functional group. Okay, so that creates small panels, 4 small panels, because we have 4 functional groups. Okay, and we set the scale on Y free. So what it means is that they are not fixed. If you don't do that, then all the y-axis will be exactly the same, which is okay, but it will kind of make some graphs too small, some graphs too big. Okay, it makes sense? So we do that, and then we have the diameter at breast height on the x-axis, so the same design, the number of trees, the frequency on the y-axis, okay, and in different colors, just to distinguish them. Okay, so here I want you to think about diameter distributions. Tell us about the forest structure. Right? We already did the look at that for all the trees, but now there are different functional groups, and as you can tell, they're not exactly the same. So some of them are look one way or the other. So here is, we probably don't have the time in the morning, but let's go through this in the afternoon. So these are all the boxes here, discussion boxes. Take a look at them and think about, you can also write code to think about this. How do you answer these questions? And also the other thing is, the other question for you is that what information is missing if we only look at tree diameter? Okay? Now, with the forest inventory data, what we can now do is to estimate a plot level biomass. The original data comes in as individual trees, but our interest is not individual trees, it's the forest. It's a collection of the trees, collection of the community and ecosystems. How do we do that? So the forest dynamic model, we need a state variable, which is the biomass variable. So state variable refers to a variable that the model keeps track of and updates through time. It's the memory of the system, where the system currently stands. So everything the model predicts next is computing from the current state variable. That's the biomass. Okay. So examples are biomass, carbon, stem density, base area, species composition. Today, we'll use above ground biomass as the main state variable. So we'll use a simplified allometric equation that are loosely based on the pantropic form of Chow et al. 2014. If you put that, that gives you the reference. It's a paper published in the Global Change Biology. So here is how we convert from the DBH measurement and wood density to biomass. So roughly, it's a coefficient, 0.1 times rho. Okay, so B is the biomass in kilogram, and rho is the wood density in grams per cubic centimeter. Density, how dense is that? It depends on the functional groups. And then last one is the DBH, how big the tree is, and then raised to 2.5 as power. So this is kind of empirical. So ecologists develop allometric equation by first cutting down trees. Actually cut down trees and then measure the size of the tree and then weight them. This is very labor intensive, right? You obviously don't want to do that for every tree that you sample, right? That's impossible. So what you do is that you take the knowledge that somebody else has built and use that, apply that to the data set. Because DBH is much easier to measure, but our interest is not DBH. Our interest is biomass, and for the entire forest. I put a box in here. This is a simplification. The public pantropic allometries also use the tree height and regional specific correction terms. We have the tree height. I simulate that in the data set, but not used in here just for simplicity. Equation 1 here omits that for simplicity. So if you want to use that for real carbon accounting, you want to consult the literature to do that. Okay? So here is the code of how we calculate plot the forest biomass and then the plot biomass. So first, let's assume the plot area in hectares is 0.25 hectare per plot. The forest biomass, so we want to focus on the forest biomass is the aggregated biomass, all the trees in the forest, okay, without considering the area, right? So the biomass typically is per area basis. If you have a bigger area, you have more biomass, right? This is not because the forests are growing better, it's because you sample more, right? So, but first to calculate that, you need to aggregate per trees, right? So this is a forest biomass. So we focus on live trees, okay? So we filter the data. So filter means that you select the rows that satisfy the condition, which is status. We have double equal here. Status is alive, so we focus on live trees, okay? Filter that. And then mutate means that you create a new variables. You create a new columns, okay? Rows, columns. You create a new columns based on existing columns that you have. Okay, so here biomass in kilogram. This is applied. Here is exactly this, right? So 0.1 times wood density, which is rho, and times the dBH in centimeters raised to 2.5. It's empirical allometric equation. Okay, and then we use that to convert this to ton. Megagram is ton. Okay, it's a more common way to do that, divided by 1,000. And then carbon is to convert biomass to carbon. So roughly half, let's assume here 47% of biomass is carbon. This is important for carbon accounting, for climate, right? So there's that. So forest biomass is, you see the unit here is kilogram, megagram. But now we want to convert this into per area basis, right? So we want to convert this to megagram per hectare. Megagram per hectare, things like that. So to do this, we group by plot ID. So now we focus on the entire plot. So each plot has 50 trees, right? So we aggregate the 50 trees in the plot, add them together, divided by 0.25 hectare. So that gets us to a unit of megagram or tons per hectare. Does it make sense? Any questions? Okay, so that's the biomass. We have the sum. So this is called split apply, split calculate apply logic in computing. So we group by them and summarize them by the sum. So I aggregate that and divide it by plot area. Same thing, we sum the carbon divided by plot area. We can also get a variable, if you are interested in this. This is basically count how many trees you have per hectare, okay? And then we say this is an additional argument that we drop the group by variable. Okay, so once you've done that, you got the new new table called plot biomass that no longer has each row with individual tree. Instead, this table only has 6 rows because we have 6 plots. So each one of them is calculated from the forest biomass, which is calculated from the tree biomass, right? So the process here, we start with tree biomass and use allometry to get the forest biomass for each individual tree, and we can aggregate that. And then we aggregate them to plot, because that is the scale of interest. Original data is collected for trees, but now we're getting to the plot. So now plot 1, we have biomass of 141 tons per hectare, carbon 66, stem density 180, things like that. This basically tells you the live trees, right? So total trees is one thing, but then the live tree is another variable. So we have plot 1 to 6. Any questions so far? Okay, so then we can visualize the plot level biomass by using create another graph, right? So now we want to create a XY graph. The histogram is only X variable, but now we want to put the X variable. This is essentially get a kind of the bar graph. The X variable as the plot ID, so that would be plot 1, 2, 3, 4, 5, 6. And then the Y variable will be how much biomass in a unit of megagram per hectare. Okay, so this basically shows that how dense the forest is. Okay, and then we put a geometry layer on that. So that generates a graph like this, plot 1 to 6, and then this is above ground biomass. Okay, so then we use the average plot level biomass as initial condition for the model, because if you remember, the model is biomass of T, right? Biomass T equals to biomass T minus 1, plus growth minus mortality minus disturbance. But to get the model, you want to start the model, you don't want to start with 0, right? You want to start some initial values. Starting 0 will be assuming that you have a bare ground, you have no forest at all, which is not the case in our study system. Okay, so this is the value that I'm going to use to kickstart the model. Okay, so initial biomass is the mean of the plot biomass of that. So initial biomass is 120. Okay, any questions? All right, so the exercise, again, we don't have time to do that in the morning, but we will spend time on that in the afternoon. The exercise I want you to do is that read the plot level biomass, look at the plot biomass table that we just simulated, and then the bar chart above this one, and think about which plot has the highest biomass, that's easy, and which one has the lowest biomass, and what functional group mix might explain the difference. Okay, this is easy. This one, you need to write a little bit code, and that is your homework, okay? Your assignment. All right, any questions before I move on to the next section? Okay. So, now we have the data, and we have done a little bit exploration of the data. We are ready to build a model. So now let's build a simple forest biomass model. The model, again, just reiterate, the model tracks the biomass through time, and that's why we call dynamics. So the model has B, which is the biomass, and that's the exact variable that we just simulated and aggregated. B of T plus 1, B of next year is biomass of this year plus what goes in, which is the growth of this year, and minus what goes out, what is lost. M is the mortality, and D is the disturbance. Okay? For simplicity, let us define the gross mortality and disturbance as constant rate applied to current biomass. So this is a very standard type of assumption that are used in forest dynamic model or in demographic model. That is, the gross component is a ratio of the biomass. It's a rate. That's why we call it rate. Okay, growth rate. It's a ratio of biomass. So G is a coefficient. It's a rate of B. And M is the mortality rate of the current biomass. Disturbance is delta is the disturbance rate of the current biomass. Okay, growth rate, mortality rate, and disturbance rate. Any questions? Make sense? So we have the flux. So we call this pool, we call this fluxes, right? Maybe I should draw in here. this is the biomass. It depends on what goes in, which is G, right? This is the growth component. And then we have something that is lost. One is the mortality, the other is disturbance. So imagine if this is like an animation. It changes over time, right? So you can have start to add, subscripts in here. What goes in, what goes out. The other assumption is that this depends on whatever that you have in time t with a rate, with a fraction. So this will be a number, I don't know, 0.2, 0.5, whatever number that you set. I want to mention this because this is important. This is the important parameter that you want to tune when you set up scenarios in our class. And then this is, mortality of B, and this is the disturbance of B. Okay? Yes? I can repeat your question.
How we measure disturbance?
Empirically, right? So if you have a large disturbance events, then you can measure what is left. Okay. So that would be, I guess 1 minus delta.
Okay.
Yeah, you can also do that through remote sensing, a lot of different methods.
Okay.
Yeah, great question. Okay, so a little bit of Amazon context. Long-term monitoring across Amazon old growth plots, such as the rainfall network. Have you heard of this rainfall network? This is one of the initiatives. I think it's started in the UK. They measure trees over time. So they actually collect the data that kind of look like the data that we just simulated. They report wood biomass growth of roughly 2 to 3% per year. So this is something that a parameter that makes sense. If you set this to 2 to 3%, that will make sense, according to rainfall network, according to their data set, their measurements. Historically, offset by mortality rate roughly of 1.5 to 2.5 per year. Okay. Studies such as Berini, this is a very influential study published in Nature 2015, find that the mortality has been rising faster than growth in recent decades. Okay, so what they are finding is that this M is getting bigger, and it's bigger than G. Okay, even without considering disturbance, what will happen? If you have M that's bigger than G, what will happen? Would you expect the biomass go up, go down? It will go down, right? Because you have more things going out and less stuff going in, right? So which is pretty important if you have that. So these are the key parameters that determines forest dynamics. And what they find back then, 2015, is that through a lot of work that the mortality is getting bigger and bigger than the growth rate. And that weakens the Amazon carbon sink. So we will use this approximate rates to set up our baseline scenario below. Okay, so how do we implement, how do we actually do this model in R? So here, what I have is I write a function. Okay, so a function is a body of code. You wrap them into a body, and all the variable here. So it will run this variable, but it's protected from the outside. Okay, so it's all local variables. So function starts with, so this is assignment of the function. Start with the keyword function. And then everything inside the bracket of the function is what we call argument. It's the things that you put into the function, okay? And then you set equal sign. This is the default argument. You can override that if you say that, oh, I don't want to simulate 50 years, I want to simulate 100 years. Fine. Then when you run the function, you will say years equals to 100. Let's give you an example, okay? So we set some parameters in here. This is kind of handy. We do it this way as opposed to write the code outside. It probably will achieve similar goals. But if you write the code outside, then every time you have to change, because as I have already hinted, we are going to play with these rates. If you want to change the values, you have to rerun the whole thing. And you can't really store it, right? But if you write a function, when you call the function, when you run the function, it's much easier. You just change that and it give you an output. So this is a technique, writing functional programming. Okay, so inside the function, we have a loop. Okay, a loop means that we do the same thing step by step, which is exactly what this dynamic model does, right? Forest biomass of next time depends on forest biomass of this time. Okay, so we have some initial value. So time is a value from 0 to the end of the year, 0 to 50 in the default. The biomass, we create a vector to store the results. And this is the length, so this is a vector. A vector is a collection of data, a numerical vector. The first element of the biomass data is the initial biomass. This is the average of what we have empirically. And then from the next year, we simulate this. Okay, so the growth, which is G in here, right? So that's G, equals to the growth rate times the biomass. So this is a little g times b, right? So basically, I mean, essentially, we are translating this into code. Right? That's all we are doing here. So there's that of time t. And mortality is the mortality rate times biomass. Disturbance is disturbance rate times biomass. And then here comes a dynamic equation, which is b of t plus 1 equals to b of time t plus what comes in, which is the growth component, minus what goes out, the mortality component and disturbance component. Okay? And after we run this iteration, we store them. That's what we call this table. And then will be the last line of a function is the return object. Okay? So this will give you the return. So if you run this function, it gives you a table, which the first variable is the time variable. The second variable is the biomass, and the third variable is carbon, which is 47% of the biomass. That has been simulated through the dynamic model, so forest dynamic model. Okay. Each passing, just a note here, each passing through the loop takes the biomass from the previous year, biomass T, apply growth, mortality, and disturbance, and then it stores result as next year's biomass of biomass T plus 1, which is equation 2. If you put a mouse cursor in here, this will give you exactly this. Again, we are translating the equation into code and applies 1 year at a time. So we do this year by year by year. Okay? So once we have the function, so run this into R won't actually give you anything because it stores the structure in R. And this is when you actually simulate them, when you run them, this is what we call, we call the function. We use the function, we apply the function. We call that simulate forest, and then you set up a different arguments in here. 50 years, we use initial value as the initial biomass, and then we say growth rate is this, mortality rate is this. And let us assume for this scenario, there's no disturbance. So I said disturbance rate equals to 0, means that there's no disturbance. And the growth rate and mortality rate are informed from the 2015 study. Okay? So when we run that, this gives us the output of a table, and that's what we call the baseline scenario, because this says that the forest grows at 2.5% growth rate, 1.8% mortality rate, and let's see what the forest looks like. So the function keeps track of the year from 0, which is the initial value, until 50, and each year it gives you biomass value and carbon value. Okay, it makes sense? Okay, so after we've done that, then we can make a graph. Wait, visualize them. Let's look at what the result looks like. And how do we make a map? How do we make a graph? We use ggplot. As you can see, it's a very handy, convenient way to do that. So the way to make a ggplot is to put the baseline, which is this table, in here, and make a graph using ggplot and make a line plot. We want to draw a line because this is a time series data, and set a line width and set a color, and then label them. Okay, so the X variable is year, Y variable is biomass. Okay, so that will give you this. And this is the result of our model, simulation model, with some assumptions. You know, we assume that this comes in, this goes out, and then we assume we have some initial value, right? So let's just call that B in here. We have some initial value in B, and then we set the growth rate I think it's 2.5, something like that, and then mortality rate 1.8, 0 in here. Okay, so that's the result, and we go forward with 50 years. Okay, any questions? How are we doing here? Okay, so again, we'll spend more time this afternoon to play with the code. So the exercise I want you to do for this part is that I set the growth rate and mortality rate as such in the code. But you can change it, right? That's the whole idea of model. You can change it and see what happens. So change the growth rate and mortality rate in the simulation. You know, think about this. What happens when the mortality is close to growth? So right now, what's the mortality rate? It's 1.8. Growth rate is 2.5. So the growth rate is higher than the mortality rate. And that is why this is going up, right? Because you have more things coming in, less things going out. Okay? What happens when mortality is close to growth? And then the other way to think about this, what happens when the mortality is greater than growth? Okay, so you can gradually increase the mortality rate, make it closer to growth, and then you can increase further. And you know, this is what the 2015 paper has found, right? So the paper said that, oh, mortality rate is increasing, and in some areas greater than the growth rate. Then what happens to the forest? Okay, so you can change that. So yeah, so that's for the dynamic model implemented in R in here. Okay, how are we doing? Do we need a break, or what do you think? Do we need a break in here? There's one more section, or we go to the. No, I have one more section. Keep on going. Okay, all right. Yeah. All right, so now we have the data. We build a basic model. Now we can change things. And this is one of the exercises in here. And then let's talk about scenarios. This is one of the important features of modeling. So let's think about different scenarios, land use scenarios. In the context of Amazon forest, so let's think about 4 scenarios that are relevant. Scenario planning means that compare plausible futures. Okay, so here we define 4 scenarios that are tied to real pressures and policy responses in the Amazon forest. The baseline scenario assumes that undisturbed old-growth forest, undisturbed, that's why I set delta to 0, right? No disturbance, 0. Current growth and mortality that are informed from the paper, from the literature. Drought mortality refers to the scenario where the tree mortality is elevated, tree mortality increased following severe drought years. For example, in Amazon, 2005, 2010, 2015 to 16, and the record 2023 to 24. These are the episodes of drought. I'm sure that you are aware of this, that happened in Amazon. So what happens to the forest when you have a drought? Do you expect an increase in mortality or decrease in mortality? Mortality will go up, a lot of trees will die, right? Okay, so that's a drought mortality scenario. Number 3, the third scenario is forest degradation. That means the growth rate will decrease. low growth rate and higher mortality from selective logging and edge effects, and plus reoccurring low intensity disturbances. So the disturbance is not zero, it has a disturbance rate, but also the growth rate decreases, the mortality increases. Okay, so the patterns that have been documented in fragmented Amazon landscapes. Conceptually, we can expect that, oh, this might be bad for the forest, right? Yes? You have a question?
Hello.
Yeah.
So in this degradation case, you have this parameter for disturbance rate,
Right.
but at the same time, growth rate decrease and mortality rate increase. So I was thinking this change in growth and mortality is because disturbance too?
It's possible, but here we separate these processes out, and we're assuming that this is the forest itself. Disturbance is a separate, is related, but a separate process in the model.
Okay.
Yeah, in a more complicated, sophisticated scenario, you can say that you can make the model mortality depends on disturbance. That's fine. It just makes things more complicated. But for now, let's keep it simple in this way.
Okay.
Yeah, good question. So, if we think about scenario 3, do you think this is good for the forest or bad for the forest? It's probably bad for the forest, right? The decreased growth and increased mortality and then increased disturbance. But quantitatively, how bad or how severe that is. Without model, you can't answer that, right? You can't answer that without a without quantification. So the model gives you a way to think about this. The last scenario is a restoration scenario. So that means if we apply certain measures or certain policies, that will increase the biomass accumulation. So this is the growth part. So they will increase the growth rate and decrease the mortality, lower mortality. So this is a typical of a secondary forest regrowth on land restored under the Brazil's forest code, this policy, and national reforestation commitments. So forest changes. That's the whole idea of forest dynamics. It changes. If we implement certain measures, that might help. So this could be good for the forest. But how good is good? How numerically do we expect that the forest restore? How long? Things like that. These are very critical questions. Without model, there's no way that you can answer that. We have to measure them empirically, right? We have to quantify that. Okay, so the way, again, in today's class, I want to set this up, is that the different scenarios, so how will we implement that? Different scenarios are mapped into different growth rates, mortality rates, and disturbance rates. Okay, so the baseline, we have already done that. It's 2.5 growth rate, 1.8 mortality rate, no disturbance. Okay, and the drought mortality is we have a slightly decreased growth rate, because if a drought, then trees don't grow as well as if you don't have a drought, right? And mortality really increased a lot. Okay, this is increased a lot. No disturbance. Degradation means that we have more. The growth is hammered even more, and the drought, the mortality rate is increased. Well, perhaps not as big as the drought mortality, but then we start to have disturbance, 1% disturbance rate. In the last scenario, restoration, here the assumption, okay, so everything here is assumption, is that the growth rate increased a lot. So we have secondary forest, and they grow really well. So 4.5% growth rate, 1.5% mortality rate, really decreased mortality rate, and no disturbance. Okay? So we set this up as a table, and then we run it. Okay, so there are different ways to run this. You can, the easy way to do this is you literally take the number here, and then call the function with these numbers, which is okay. But here I want to introduce a more advanced way to do this, more efficient and advanced way to do this. So what I did is I map the parameter value. So basically what we want to do is that we want to take out the first row, the first scenario, and apply functions to that. Apply this to the function, right? And then we take the second row, apply to the function and see what happened. Third row, apply to the function to see what happened. You can do this manually, but we can also do this using the PMAP. So there's a parallel mapping of the list of the rates in here. This is called lambda function without a name. And then to the function that we just created. Okay, so it pipes in so we simulate 50 years. We have the initial biomass, which is a constant that we just created. And then we apply growth rate, mortality rate, disturbance rate. Okay? And then we select the variables, we select the scenario and output, and unnest this. So this is the nested list. So that will give us the following. So it will give us a long object where the first column is the scenario, the second column is the year, the time step of that scenario, the third column is the biomass, the last column is the carbon. So the last two are the results that we run the model with the particular set of parameter values. Okay? So a little bit technical detail in here. So the PMAP function calls the simulate forest function that we wrote. So PMAP is a built-in function in PURR, P-U-R-R package, that calls the simulate forest function that we wrote, customize the function, once per row of the scenario. And it feeds in that row's gross mortality and disturbance rates that we set up in the scenario table. So writing the simulation as a function once I'm mapping it over scenarios is a very efficient way to do this, as opposed to copy and paste many times of the function. We have 4 scenarios in here, which is, if you want to copy paste, that's fine. You do it 4 times. What about if you have 100 scenarios, right? You don't want to do that, copy and paste 100 times, right? So I'm just telling you the efficient ways to do things, to run the function. Okay, so after that, we can make a graph, right? So every time we run something, we get numerical results. It's more intuitive to make a graph of that. So we can plot the biomass trajectories. So trajectories refer to the change over time in a graph. So here, again, we use ggplot to visualize the results. We map the aesthetics. So now X variable is year, Y variable is the biomass that we simulate. And now we use, because we have 4 scenarios, I don't want to lump them together, it doesn't make sense. We want to plot different trajectories. And here I use color to represent trajectories. So here the color is the scenario. Okay, I create a line and I put a theme and label in here. So this is the graph that we can create. So here the axis is the year, which is 0 to 50, the simulation year that we have. They all start with the same value. They all start with the initial biomass that we created in the beginning, right? So that's why on the left-hand side, on the left, we have a single point in here. The y-axis, the vertical axis, is the above ground biomass. And then different colors are different scenarios. So what can you see in here? What can you tell in here? How many lines do we have? We have 4 lines, right? And then the top line, this purple line, is which scenario? It's the restoration scenario, right? So as we expect, when we talk about these assumptions, we think about, restoration seems to be good. That must be doing good for the forest. This shows you how good that is. Okay, so this shows you the dynamics, right? And the second line is the baseline, right? The red is the baseline. So that kind of grows, but slowly. And then this green, two grids. There's one drought scenario and then one a degradation scenario. So that actually goes down. So that means the forest is if you imagine that there's a horizontal line, these two other scenarios goes below the horizontal lines. So the forest is actually not, it's getting worse, basically, right? So that shows you that. You can also do this using carbon, right? And basically just swap the biomass variable with the carbon variable. And this, we have this simple assumption that the carbon is a fixed ratio of the biomass. So when you plot that, the shape of the graph will look very similar to biomass because that's the fixed ratio on that. The difference is that here we have the y variable with the above ground biomass. Okay? Any questions? Okay, so I hope this is transparent enough that you can actually run the model and play with the different parameters, different rates in the model. Okay, so what I want you to do for the exercise is that add your own scenario. So think about what scenarios that you are most interested in. Okay, so add a fifth row. We have 4 scenarios in the materials that I have, but add a fifth row, another row in the scenario triple with the gross mortality and disturbance rates that you think represent a plausible Amazon land use pressure, the kind of research question that you are interested in. For example, selective logging, fire. We haven't talked about fire yet, but think about fire. What kind of rates that the fire will impact? Agroforestry, for instance. And then rerun the code, use PMAP to map the parameter values to the function, and then call the biomass plot above. So where does your scenario fall relatively to the other 4 scenarios that we have here? Okay, so keep that in mind and think about, these are also assumptions. Think about what assumptions that you are making, and we will do that in the afternoon. So with that scenario, we can compare their outcomes. We compare scenario outcomes. We can summarize the final biomass and carbon after 50 years, okay, which basically means that if you have this, so tell me what's value in here, what's the value in here, what's the value in here, right? So summarize that. So we can do this by by filtering out the last row at the end of the simulation, which is year 50, right? So this means that let's filter the data, the table that we created, the results that we created, with the year equals to the maximum year, which is 50, and then we order them by descending order of the biomass. So not surprisingly, as expected, this will order the restoration on the top because that's the sort of best scenarios that we have in the 4 that we set up. So the biomass that we have is 527 carbon as such, and then the baseline, and then job mortality, and then last the degradation. Okay? And then we can visualize them, we can make a graph of that, create a bar graph, and so we can say that now the x variable is the scenario in here. I revert the order, I flip the coordinates. So it's the scenario here, and the y variable is the biomass, and the field, the color is the scenario, and create a bar graph and flip them because kind of looks a little bit nicer. You can plot that in the other way, but it looks nicer to put the bar horizontally. So this shows you how much biomass that we have in the restoration scenario, and then in the baseline scenario, job mortality scenario, and degradation scenario at the end of the simulation at year 50. Okay? Any questions? Yes, please.
I have a question about it. I just started to writing about this theme, and I'm thinking, how can I use abundance data on these scenarios? Because I planning to work with some scenarios to a group of insects, and I want to know how can I use this type of data on this analysis.
So you're saying you have insect data?
Yes.
How do you use that in the model?
Yes.
Is that your question? So then I want to turn the question to you. What do you think the insect affected the forest community or forest ecosystem? Right? Does it affect the growth rate? Does it affect the mortality rate? Does it affect disturbance, or does it affect something that we don't have in the model, and then you can add them in, right?
Okay. So for instance, I can use a model to see what will happen with this community in some simulations, like a drought disturbance or more raining, this type of climate changes.
Right, yeah.
I can create these scenarios on this type of analysis.
Yeah,
okay.
so I have other projects look at well, not in Amazon, but in boreal forest. We have a lot of remote sensing data to tell us about the insects as a disturbance. So in my case, I would think perhaps this is most relevant to disturbance.
Okay.
Right.
So it's possible.
Oh, sure,
you can
yeah,
use this type
everything's
of data.
possible.
Okay. Thank you so much.
Yeah. Okay, so after you've done this, here are the discussions, questions I want you to think about. Which scenario produces the highest biomass after 50 years? I think I probably already answered that, but think about this. Which scenario produces the lowest biomass, and which parameter changes appear most important? This is a kind of interesting question. What you need to do, I'll give you a hint here, is that you need to rerun your model and see which parameter is the most sensitive to the results that you will have, right? And sometimes we call this sensitivity analysis, and there are different ways to do this. But the simplest way is that you can manually do that. You can set up different scenarios and set a range of parameters and see how sensitive that affects your results, okay? And then perhaps this is most relevant to your specific question or project. What data would we need to make these scenarios more realistic for a specific Amazon landscape, right? So we just heard a great question on insects, right? So we don't have insects in here. How do you think about the insects as maybe as a disturbance or maybe as another biological agent to influence the Amazon forest, right? So really, the goal of this teaching material is not for you to exactly copy what I have here. It's for you to think about creatively, how do you use that? How do you adapt this for the questions or projects that you want to work on? Okay, so briefly, I want to wrap up for the morning session in here. So let's briefly think about interpretation. So this model is, as you can see, is a very simple model. It illustrates several important modeling ideas. So in reality, you might play with very complicated models, but the basic principles are the same. So first is the model assumptions. Every model is a collection of assumptions. Okay, so it includes assumptions. So here are the assumptions that we are making. We assume that the growth rate is proportional to biomass, right? So this is our assumption. We assume that the mortality rate is proportional to biomass, right? So that's it here. We assume that the disturbance removes a constant fraction of the biomass. That's why we have this formula. We have delta times B, right? And whether or not that makes sense, you need to think about this. If they make sense, that's how you implement that. So we have another question of, would this depend on that? Oh, sure. It's totally possible, but not under this type of setup. You have to change it. I actually would encourage you to think about how you change it to make it more realistic, more tailored to the questions, to the research questions that you want to ask. Okay. The fourth bullet point here is that the rates remain constant through time, which is also an important assumption that we are making, right? So constant means that I don't have a subscript t in here, right? So g is set as a constant, 2.5 or 2.0, something like that. But in reality, this might be different, right? So the growth of we just mentioned the paper published 2015. What they are claiming is that the mortality rate is getting higher and the growth is getting lower, right? So that means this is not a constant, but you can change that. Our model has the capacity to do that. When we write the governing equation, it doesn't say that this has to be constant. It did not say that. And this is a simplified assumption that we are making. But you can make it more realistic and complicated, okay? And the last one, the forest is represented by one biomass pool. So far, everything that we talk about in this notebook is that B is everything that we care about for the forest, which is above ground biomass, which is calculated from the DBH using allometry, right? But we know forest has roots, has below ground, has other components of the forest, and sometimes researchers are also interested in how you partition the biomass in different pools. How much goes to leaves, how much goes to the stem, how much et cetera, et cetera. So if you want to make it more complicated, you can say let's build a model with not just one pool. This is one pool, right? Let's build two pools, above ground, below ground, and see what that changes. Maybe some processes can benefit the forest in one pool and not in the other pool, which is also possible. So here are all I think this gives you a lot of ideas of how you advance your research. You think about how do you make a sort of simple model more realistic. So these assumptions make the model transparent, but they may also limit how realistic they are to the actual ecosystem. The second comment I want to talk about is the scenarios versus predictions. The goal of this model is not to say the forest will have exactly this much of biomass in 50 years. We have the numbers, but the goal is not to say this is, let's look at the crystal ball and predict what happens in 50 years. That's not the goal. The goal rather is to ask, how do the outcomes differ under different scenarios, on the drought scenario, degradation scenario, restoration scenario, comparing to an undisturbed baseline, right? Relatively speaking. Okay? The other comment that I want to make is that let's think about when simple models are useful. A simple model can be useful if it matches the question. Okay? Always think about the question. For example, this model may be useful for teaching scenario as we are doing here today, or comparing broad policy assumptions. It is not sufficient for detailed carbon accounting, species level conservation planning, right? So we don't have a species information in the model, or regulatory reporting. Okay. So I want to put a caution box in here. Do not use this workshop's rates or outputs to justify a specific conservation or restoration decision. These are approximations. When you have real policy and management decisions, they should rely on site-specific inventory data. You should get some real data for that. And validated allometries. Okay, so how do you convert the DBH into biomass? This depends on allometry. And if your allometry is not correct, this can be off by a lot. Okay, so be careful about that. And then peer-reviewed model parameters. So if you think about different scenarios, you want to be more thoughtful about what numbers that you set. Read more papers on that. Okay. The models have limitations. This simple model does not include species differences, tree size structure, recruitment, age, or successional stages, drought timing, fire spread, spatial heterogeneity, uncertainty, and feedbacks between forest and climate. And more advanced models can include some or all these processes. Okay. So here is the discussion I want you to think about this afternoon. So look back at the scenario that you added earlier, the 5th row that I asked you to do. Be creative on what scenarios that you want to add. Which of the assumptions or limitations above would matter most for the scenarios? Okay, would addressing it push your scenarios biomass trajectories up or down? So that means in thinking about this, maybe some components that you have and some components you are missing, right? And then can you go back to the scenarios that you design and change it, tweak, adjust it, so that it can get closer to the questions that you are interested. Okay. So finally, I want to end up with some key takeaways. So we focused on forest dynamic models, which represent change through gross mortality and disturbance, right in here as a simple model. We use the inventory data to define the initial state of a model. Okay, that's the initial condition. Everything starts with the same initial value. Scenario models compare plausible futures. We have the drought scenario, degradation scenario, restoration scenario. They are not meant to predict one exact future. Okay, the rates really matter. I hope you will explore that this afternoon when you code up your own model. What you will find, at least this is my experience, that even a small change, 1% or even a tenth of a 1% in growth and mortality, they compound, because this is essentially a compounding model. It may not matter too much in one single year, but we are talking about 50 years in simulation, or maybe you want to change to 100 years. The compounding effect is huge. Okay. The compounding effect. That's why the publication, I just mentioned the paper, 2015 paper. They conclude that the rate differs. You might say, 1%, 2%. That doesn't seem to be too much, but if you compound this over 50 or 100 years, that's going to make a huge difference. Okay, they compound substantially over decades. The model assumptions should be explicit. So whatever that you think about ecologically, they need to be implemented, in the code. They should be discussed and tested against Amazon-specific data whenever possible. Okay, so think about when you make these assumptions and how realistic they are, and if you want to make changes to this adjustment to that. Okay, any questions? Yes, please.
Hello.
Yeah.
You said this model was not designed to predict future biomass, for example, but you could do that? I mean, to build a model to predict this?
Yeah, sure. You can do that. If you feel comfortable that all the assumptions that you put in are realistic to your study system, yeah, you can certainly do that. All right, so that concludes this morning session. And so again, we'll work on the specific code, and also for the YouTube audience, everything is available in both English and Portuguese. You are more than welcome to work on that. And my hope is this is gives you a starter, but really you need to build your own thing based on that. Okay? All right. Thank you very much.
Thank you, Kai.
Pessoal, então a gente encerra a sessão agora, lembrando que 13h30 a gente retorna, vai ter a parte prática, e depois às 3h30 a gente começa a parte dos grupos. E a gente vai passar já para vocês o modelinho do PowerPoint que precisa ter para sexta-feira, bem como a ordem das apresentações. É bem possível que na sexta-feira a gente vai começar às 8h30 para ter os 15 minutos aí de apresentação, dividido / em perguntas. Então, deve ser de 5 a 7h30. Tá bom? Obrigado, gente. Bom almoço.